recalculate the averages and all of that, and I'll send that out. Okay. Don't worry. Don't worry. Enjoy your lives while you guys are young. Right? This is college. This is like the best years of your life. Okay, it's only down that hill from. I'm kidding.
But not really.
Huh?
But not really.
The first few years of marriage is really awesome too. So. All right. If you choose to get married, and maybe not everyone. Okay. Anyway, chapter 15. All right. So we talked about probability of A or B, and the resulting thing is probability of A plus the probability of B minus the probability of the overlap, A and B. Okay. I think in chapter 14 your homework only covered the mutually exclusive cases without this probability of A and B. Okay, but now, but I covered this on Wednesday, and we have that. So, you know, if I say the probability that someone owns a car is 90%. And the probability that someone owns motorcycle or motorbike is 12%, and the probability that someone owns both motorcycle and a car is 9%. Make sure this ends up. Okay, so what would be the probability of someone owning a car or a motorcycle? Right, and then I'll ask, what is the probability that someone owns a motorcycle and no car? And what's the probability that someone owns neither car nor cycle? Go ahead and take a moment to figure out the answers to that. And so what do we have here? Or do you guys need another minute? Okay, so we have 0.93. Yeah. 0.90 plus 0.12 minus 0.09 gives us 0.93. Okay, so motorcycle and no car. We can draw our circles. So this is car. This would be motorcycle. The total area inside the car is 0.9. The amount in the overlap is 0.09. Okay? So if the total area inside the car circle is 0.9, I would have to have how much over here? 0.81, right? And then total area inside the motorcycle circle is 0.12. And if I have 0.09 here, how much do I have over here? 0.03. Okay? And so that would be the answer to our car. Having a motorcycle and no car, 3%. And neither car nor a cycle, that would be everybody out here who's walking or taking public transit. because everything has to add up to 100%. So. Because everything inside the double circle is 0.93, so maybe I could just do 1 minus 0.93. Is that good? Okay. So you guys have a few problems in your homework, going over that stuff. I know I did this really quickly, but I feel like we talked about this already, so. I know we did talk about it already, so. Okay, and then we have the general multiplication rule. Alright, so we have the probability of A and B is equal to the probability of A times the probability of B given A. So this is read as probability of B, why am I writing this? B given A. So this is always true. Last week you learned the special case when A and B are independent, then you have probability of A and B is equal to the probability of A times the probability of B. Okay, so this is a special case, but that only applies to independent events. This is always true, okay? So this is always true. So the probability of A times the probability of B given A, all right? So the answer, so what is the probability of B given A? The answer ends up kind of cyclical, but so the probability of B given A is equal to the probability of A and B divided by the probability of A, okay? But you can see that that's silly because all I've done is divide both sides by the probability of A, and now I'm left with the probability of B given A. But this is the definition of a given probability. And so, because this is true, then this is obviously true, or because this is true, this is true. So it's all I've done is just rearrange the terms, but this is the definition for the probability of B given A. Now the labels for A and B are arbitrary, and it's good to keep in mind that the probability of A and B is exactly the same as the probability of B and A. There's absolutely no difference between saying A first and then B, or B first and then A. Okay. But if we were to flip the labels around, we get something different. If I say, what's the probability of A given B, then on the top we still have the probability of A and B, but then we're dividing by the probability of B. Okay? So all I'm doing is I'm just switching labels around. Okay, so let's just try a simple word example of what this means. So let's say the probability that there is a storm tomorrow is, I don't know, 20%, okay? And if there is a storm, probability of a power outage is 30%. Okay. So what is the probability that there is a storm and a power outage? Well, from the statements I've written, the probability of a storm is 0.2, and the probability of an outage, and it says if there is a storm, so that's on the condition that there is a storm. So the probability of an outage, if there is a storm, or given a storm, is 0.3. So the probability of a storm and an outage would be 0.2 times 0.3, 0.06. This, we can make things more complicated with, say, a tree diagram, okay? So let me just add one more thing, and then we'll say if there is no storm, the probability of an outage is 5%. So if there's a storm, there's a 30% chance of an outage. If there's no storm, a 5% chance of an outage. All right. So, what would I write to say is equal to 0.05? I would write probability of outage given no storm, right? So I could ask the question, what's the overall probability of just having an outage? Okay, so the answer to that may not be as straightforward as you might think. Okay. So I'm going to draw a tree diagram. And in this tree diagram we say there could be a storm or there could be no storm. What is the probability of having a storm? We say 20%. So if there's a 20% chance of a storm, the probability of having no storm is 80%, right? Okay. If there is a storm, what's the probability of an outage? We said 30%. And so the probability of no outage, if there is a storm, would be 70%. So keep in mind that this 30% is probability of outage given storm, and this is probability of no outage given a storm. And if I multiply down the lines, I would get 0.06, and that's the probability of a storm and outage. And over here, 0.2 times 0.7 giving me 0.14. This is probability of a storm and no outage. Okay, so go ahead and, well actually I'll just fill it out for you because I think we're going to run out of time. So on the bottom branch, this is what happens if there's no storm. We could still have an outage, or there might be no outage, okay? So if there's no storm, what's the probability of an outage? We said 5%, right? So this is probability of outage given no storm. And over here, I would then have what? If there's no storm, what's the probability of not having an outage? 95%, right? Because when there's no storm, either two things can happen. There's an outage or no outage. Probability of an outage is 5%. Probability of no outage would be 95%. Okay. So anytime you have a node with branches coming off, you know that the branches have to add up to 1. Okay. So this would be probability of no outage given no storm. And then if I multiply down the lines, 0.8 times 0.05 gives me 0.04. That is the probability of no storm and an outage. And over here I would have 0.76. This would be the probability of no storm and no outage. Okay. So make sure you know the difference between when it says and versus given. There's a big difference. Is this tree diagram okay? All right. So then what's the overall probability of having an outage? Okay. So there's two ways to have an outage. Okay. This would be the probability of having, we could have an outage when there's a storm, so storm and an outage. Plus, we could also have no storm, but still end up with an outage. So there's two ways to end up with an outage. This is 0.06, this is 0.04. So we have total probability of an outage is 10%. Alright, and then so our last thing that I'm going to cover here is what do we do, what if I asked, okay, let's say, I don't know, you're hanging out in the basement, so you have no idea what's happening in the outside world. But the power goes out, so you know there's an outage, okay? And you say, oh, I wonder if there's a storm out there. So you ask, what's the probability that there's a storm if the power has gone out? Okay. So what's the probability of a storm given an outage? Okay, so this is different from outage given storm. Or here now we know that there has been an outage. I'm asking what's the probability that there was a storm? Okay. So when I say there's an outage, we are limiting ourselves just down to this possible situation or this possible situation. So let me just use the formula, and I'll say storm and outage divided by probability of an outage. So in the denominator, I'm going to put 10% probability of an outage, because we're limiting ourselves just to this situation where there's an outage and this situation where there is an outage. Either there's a storm and there's an outage, or there's no storm and an outage. Okay. And of those two situations, the one that corresponds to a storm and an outage is 0.06. Do you see that? So an outage should happen only 10% of the time. But if it did happen, then 0.06 of that happens with the storm, and so this becomes 60%. So the probability that there was a storm given an outage, 60%. Okay. This shuffling around of things using a probability tree to answer questions like this, that's known as using Bayes' rule. That's not so important, just the idea and methods of doing some of this.